Well, as exciting as all that is, so we're going to move on and talk about magnetism. Yay. So we're almost done. Kind of been tiptoeing around, basically moving kind of slowly. But that's okay. So, guys, y'all's talking now. Hey. So one of the things that we left with last time is talking about a charged particle entering a magnetic field. And we use our right hands, so we got our right hands ready. All right, there we go. And we can know what direction the force would be. For instance, when this proton, which is positively charged, gets launched into a magnetic field, what do these X's mean? Does that mean it's going into the plane or out of the plane? It means it's going away from us, so it's into the plane. Again, the X's are like the back of the fletching of an arrow. So if the arrows are going in, that means our magnetic field is going in, our proton's going this way. That means it's going to feel a magnetic force, F sub B, in the vertical direction, because that's our thumb. So fingers into the board, these are our palm fingers going into the board, direction of our current flow is that way, magnetic field is that way. And then we learn something pretty important, and that is the acceleration that the force is going to provide. Remember, acceleration is going to be proportional to the magnetic force. Okay? And the acceleration that the force provides is going to be how compared to the velocity. The velocity and acceleration are going to be what?
Inverse.
Not inverse, but in their direction they will be perpendicular, exactly. So they're going to be perpendicular to each other. They have to be, because they're three different dimensions. So if you have a y force and an x velocity and a z magnetic field, they're at 90-degree angles. So your velocity and your acceleration are perpendicular to each other. And that's significant because in order to do work is force times displacement. In order to do work, force and displacement have to be in the exact same direction. Or there has to be a component of one in the other direction. In other words, you can use an angle if you have to. But in this case, if they're perpendicular, if the force is perpendicular to the displacement, then the work is zero. The work is zero because the movement is this direction, the displacement is, in this case, right, and the force is vertical. They're exactly at 90-degree angles, which means the work that the magnetic force does on the particle is zero. And that's important because that means what can't happen?
Can't have velocity.
It can't have increasing velocity, exactly. It can't have increasing velocity. If the work is zero, then the magnitude of the velocity can't be increasing, because if the magnitude of the velocity increases, what's increasing?
The work done.
The work via KE, kinetic energy. If the velocity is increasing, that means the kinetic energy is also increasing, which means the work is increasing, or there's work being done. If the work is zero, that means the kinetic energy has to be constant. And if the kinetic energy is constant, that means the magnitude of the velocity must also be constant. Capiche? Verstehen? Comprende? Understand? Okay. Kinda. You're getting there? All right. Anyway, it's important in that the direction of velocity is changing, okay? Because there's an acceleration. That acceleration is creating a change in direction, but it's not creating a change in magnitude. And what kind of object do you have when an acceleration is perpendicular to velocity, but the velocity is not changing its magnitude? A circle. Okay. You have a circle. If you have a constant velocity, but the acceleration is perfectly perpendicular to the velocity, if your velocity is like that and your acceleration is like that, you're going to have a circle. That's still amazing. Do it again. Well, the problem is you have to go really fast, so the ink, it runs out. So you have to go kind of fast to do it. If you go slowly, you'll try to fix it as you go. You don't want to fix it as you go. Okay. Lock your elbow and go around. Anyway, so it makes a circle.
But you could lock your elbow and so good.
That's true. That's why you don't want to look at it. You're like, ooh, done. All right, so there you go. Making circles, 101. You come back, roll that back, circles. Hey, does that idea make sense?
Yeah.
Okay, if this, any questions so far? Question?
It's only a circle.
Yes. That is kind of the definition of a circle. When the thing that's making the line and the thing that's changing the direction of the line are perpendicular, you get a circle. If they're not perpendicular, you get an oval or an ellipse. But if they're always perpendicular, you'll make a circle. You always make a circle. Other questions? Okay, if there are no questions, let's review our two equations that we've learned so far for magnetic force. One, FB, is QBB, and one FB is BIL. What's significant about these two equations? They're the same thing, exactly. They're both Coulomb meter per second Tesla. Okay, they're both Coulomb meter per second Tesla. The difference is you use IL when you have charge, when you have a current of charge traveling along a wire, and you use QV when you have a single point charge traveling through a field. But they are exactly the same. They're Coulomb meter per second Tesla. Tesla Coulomb per second meter. They're the same thing. Okay, so let's use these equations in a button that might be working. There we go. Okay. An electron that moves with a speed of 6 times 10 to the 4th meters per second, perpendicular to a uniform magnetic field of 0.8 teslas, experiences a force of what magnitude? Now it doesn't ask for the direction, all it wants is magnitude. So find a formula you like, plug the numbers in, and figure out what your FB is. Yep. B is magnetic field strength. F sub B is the force that that magnetic field creates on that charged particle. Like this one.
Yes. What? I need my calculator. My What? 7.68 You're not even the.
Hey guys, I gotta tell you, especially in the back row, that's not a big issue in the front row, but for the guys in the back row, I'm fairly certain I am really good at hockey. I think if I had to like play hockey at the professional level, I could handle myself pretty well. And you know why? This last Saturday, I watched a game between the Boston Bruins and the Blue Jackets. Anyway, between the Boston Bruins and the Blue Jackets, and I had a pretty good idea what they were doing as I was watching. Like, yeah, all that makes sense. So I'm pretty sure that since I watched them and everything made sense, I'd be pretty good if I actually had to play hockey myself.
I did it.
Oh, good.
That
is my story. It's for the benefit of the people who aren't actually doing anything. So like, I'm just gonna watch Mr. Byard. Okay, that makes sense. I'm good for the assessment. I'm ready to go. Give me a quiz now. But I've watched teachers do all this work. I'm pretty sure I'm pretty good at it. Because I watched them and it made perfect sense.
It's you too. For us, not so much for us. I'm like,
Hey, what did you put in for Q for the electron?
1.6 times 10 to the negative 19.
Yeah, you just use the fundamental charge 1.6 times 10 to the negative 19 coulombs. And for V, you use 6.0 times 10 to the negative 4th, sorry, positive 4th meter per second. And look at me running out of space. And you multiply that by equating 0 Tesla. Yeah. Yep.
What?
So a question was asked, is it going to be negative? It is going to be negative, and what the negative force tells us is it's going to, if the thumb is positive, then negative thumb, you're negative, the opposite direction. So if it asks us for direction, you'd be like negative thumb. It would be big.
Can I
Positive
say
thumb,
negative thumb?
negative thumb.
Say negative thumb for the direction.
No, but if it gave you the direction, you could say like the opposite of what the right hand rule would tell you. So what is the magnetic force in this exercise?
Negative 7.68 times
7.68 times 10 to the negative
15.
negative 15 newtons. Now, that seems like not a lot, and it isn't. Okay. Oh, I'm sorry. You still have a lot of things to say? So, if you understand where this comes from, give me a thumbs up. Okay. Not a big number. This is a very small force. But keep in mind, electrons are very small particles. So, if I was to tell you that the mass of an electron is 9.11 times 10 to the negative 31 kilograms, could you tell me what acceleration that electron would experience? Sure.
Yes.
Why don't you go ahead and calculate that? How much acceleration would that electron experience? By the way, m sub little e is the mass of the electron. 9.11 times 10 to the negative 31 kilograms.
Single electron?
Uh-huh.
I know that I should know this, but the 1.6 times 10 to the 99 is just the charge.
It is the fundamental charge. So this is what Millikan came up with when he did the oil drop. This is the fundamental charge, or the smallest charge that can exist. It's the charge on a single electron or a single proton. 1 and 2. Okay.
Was this the, are we using the force that we just found?
Yes.
That you wanted us to do? Okay.
Yeah. Because it's the force on an electron.
So it says E minus. Is that showing that the number is negative?
No, the E minus is the electron.
Okay. But it is a negative number.
It is a negative charge, yeah.
Why is it not written?
This should be a negative right there. Because I'll just pretend that that's there to check your knowledge. But yes, it should be a negative. Okay. And Audrey, you had a question?
I was just going to say, do we need a number?
No, it's on your green chart. Yeah. The fundamental charge is on your green chart. Okay, so the acceleration of our electron, I'm just going to say A sub E because that's fun. What is the acceleration of the electron?
8.43.
Times 10 to the big 15 meter per second squared. Oh my goodness. So 8.43 times 10 to the negative, or 10 to the positive 16 meters per 15 meters per second. So the electron,
Wait, shouldn't it be negative?
nope. You have a negative 31 and a negative 15. So F equals MA. So F equals M. So A is F over M.
Right, but that negative 7.68, wouldn't that change things for the coefficient?
Oh, you mean negative up here?
Yeah.
Yeah.
Yeah. Okay, yes.
It's going in like the same
Yes,
direction.
I'm sorry. I thought you were negative X1.
No, you're
yes, negative right there. Okay. So what does this mean? It means when you fire it, you fire the charge at the television screen, it experiences an acceleration away from the center line. So you're basically painting the television screen. The old TVs, remember the old round glass TVs that your grandparents had, your great-grandparents, your great-grandparents? So the electrons would be fired at the screen and they would be deflected with an acceleration that was pretty significant. That's a huge acceleration. And it has to be a huge acceleration because the electrons are moving really fast. I mean, in this case, they're moving at 60,000 meters per second. So they're moving really fast. So they do experience a large acceleration. And do you want to do the kinematics to figure out how far they would move in the time it takes to hit the screen, or you just want to move on to mechanics?
Let's find out.
Move on.
Do I need it?
No, your test is only second semester.
Oh, good.
Oh, good.
Yeah.
Really?
No throwing baseballs or launching cannons or anything.
Oh, good. I hate
Yeah.
that. Oh my god, I forgot that was this year.
I'm so
I don't know why, but I thought that was last year.
Okay.
No,
I hope that makes sense.
Let's do this again. A 0.8 meter wire segment carrying a current of 0.25 amperes oriented perpendicular to a uniform magnetic field of 0.5 teslas experiences magnetic force of
You don't actually want to laugh. You just are. No, I do. I love laughing.
I love to laugh.
What was that?
It's a song, okay?
It's a classic song, a classic. Very
It's from every performance.
Oh, I know the song.
It's Uncle So-and-so. He's like floating around in the road.
I just didn't know why it was happening.
No. Are we gonna have a review of it before this?
By general philosophy, no, but we'll see. I don't like to do reviews, and the reason I don't like to give reviews before big tests is what usually happens is I give you a series of concepts, and you memorize the concepts, assuming that your test will be memorization. And it isn't. Your test is not memorization. Of the 70 multiple choice questions, about 35 are math. You can't memorize math. So it's basically practice. Your review is what you have in front of you. What we do in class and your worksheets and your labs. So we'll see. And again, in general, I really don't like giving you review sheets. I guess it works in some classes where you're asked to memorize a bunch of crap, but that's not productive in chemistry, or physics.
Are you still gonna like post the list of like concepts that we should study though?
Oh, absolutely.
Okay.
Yeah. I'll even tell you how many of each question is on the semester test, or how many of each concept. Okay, so let's plug our numbers in. So now we're using a current carrying wire, so what formula are we going to use? BIL, yeah. BIL. So this wire is experiencing 0.5 teslas, a current of 0.25 amperes, and a length of 0.80 meters. So what's the force that that wire encountered?
0.1.
0.1 newtons? If you say so. Okay. How are we doing about this stuff? Good? Move on. What force would the above wire experience if it was parallel to the magnetic field?
No force.
Zero. No force, exactly. Zero. Okay? Because these are vectors. So the force is a vector, the magnetic field is a vector, and the current or the length together are a vector. Okay? Travel of charge is a vector. So if you have them parallel to each other, you don't experience the force. If your architect put the power line parallel to the Earth's magnetic field, it doesn't hum. If it puts it parallel or perpendicular to the Earth's magnetic field, it hums. Okay. And lastly, what force do neutral particles feel? None. None. Because there's no charged particle. So in broad strokes, a magnetic field does not affect neutral particles. Okay. Give me a thumbs up if you're ready to change gears and talk about something else. All right. Speakers. So how do speakers work? Well, a loudspeaker, they call them loudspeakers because I don't know why they call them, they're just speakers, basically work the same way. They have a coil of wire, and I tried to take the speaker apart, but it was not to be. So if you've never seen a speaker before, this is what they look like. There's a flexible membrane below the cone, and the cone is what creates the air shock wave. Okay, we learned that sound waves are what kind of waves? Longitudinal waves, which go out. They go shock, 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 shock. So basically, a speaker is a very, very simple device, and all it is a coil of wire that acts like an electromagnet when there's current going into it. Okay, so an electromagnet is a temporary magnet that's just made of a coil of wire. And when the current is going through the coil of wire, the magnetic field of the permanent magnet repels the magnetic field of the electromagnet, and that causes the cone to go out. So if you give it a positive value, there's a magnet in here that's a permanent magnet. It's got a magnetic field, and when a current goes through the electromagnet, it creates a magnetic field that pushes against the permanent magnet. And that causes the thing to go out. And then when a negative current hits the magnet, it pulls it back in. It's attracted to the magnet. Repelled, attracted, repelled, attracted, repelled, attracted, repelled, attracted, repelled, attracted. So to make a shock wave, you need a compression and a rarefaction. The compression comes from positive voltage in the electromagnet, and the rarefaction comes from negative voltage in the rarefaction. And that's how they work. It's just what electricity goes in, and the timing of the positives and the negatives causes the speaker to move. Yeah.
What causes a speaker to like blow out?
If there's too much current, and you basically overwhelm this membrane. So this flexible membrane, this one's fabric, made out of some sort of fabric. This membrane can basically holds the speaker so it doesn't go too far in or out. If you overcome the membrane, you produce too much force, then with too much current, then you can blow it out and the membrane will break and the magnet will just kind of go too far and it'll no longer be in the influence of the original magnetic field. So that's how they work. So there's the membrane, here's the permanent magnet right here, and then inside the permanent magnet around here would be a coil of copper wire. So there's a coil here, a coil there. And as the current goes around this coil, it produces a magnetic field that simply opposes the permanent magnetic field. That's how it works. Okay.
What would happen?
Questions?
What would happen if you put a magnet next to a speaker? Like a powerful magnet.
A good question. If you put a really powerful magnet in front of the cone, probably nothing. But if you put a really powerful magnet behind the cone, it could actually demagnetize the permanent magnet. I actually have some magnets that have been ruined because they were too close to more powerful magnets, and the more powerful magnets realigned the magnetic domain to the permanent magnet, causing the permanent magnet to no longer work anymore. So if you put a permanent magnet in the dome, probably nothing. But if you put a really strong permanent magnet behind the magnet, it could actually demagnetize the permanent magnet. And without that permanent magnet being there, no magnetic force. Okay? So far so good? Okay. Railguns, coil guns, and Gauss guns. Stuff of science fiction, sort of. Okay, so a conventional weapon, a conventional gun, basically takes a bullet and puts behind the bullet some explosive material, and then that explosive material explodes, creating hot gases, and that forces the bullet down the barrel, those expanding hot gases. What a railgun does is it drags a piece of metal mechanically with a magnetic field. So instead of using a chemical explosive, boom, it uses a jet of electricity down a rail, and the magnet basically drags the bullet down the rail, much like a magnetic train is dragged down the rails. They work like this. So this is the railgun, and what happens, if you use your right-hand rule, is as the current goes down the coil, that creates a magnetic field this way. And the current goes up this coil, that creates a magnetic field this way. Both of them work together to produce a magnetic force on whatever metal you have between the rails. Can you see that a little bit in your mind's eye? So current goes down the rail, it spins around the rail this way, up the rail this way, spins around the rail this way, and the magnetic field between the coil is out of the plane, if you will. The magnetic field, in this case, is out of the plane. That produces a magnetic force on this current carrying thing. So out of the plane is, out of the planes are dots or X's?
Out of the plane?
Out of the plane.
Dots.
Dots. So you can kind of see it's out of the plane here, and can you kind of see this? The upper wire is out of the plane, and the lowest wire is out of the plane this way. So you have a magnetic field that is out of the plane between the rails. Give me a thumbs up if you can see that so far. That's step one in making a ridiculously destructive weapon. Okay, so you got an out of the plane. Now the current is going this way. So the current's going down across the metal thing this way. So the current is going this way. I know it's at an angle. That's the best. This is the best diagram that I could find. It was simple. So the current's going this way. So you have a magnetic field that is out of the plane, like so, and the current is going this way, like that. So the force is like that. So you have a current carrying device, usually aluminum, because aluminum carries current, but it is itself not magnetized. So the magnetic field is created as the current travels through it, electricity goes to this rail, and the rail gets launched extremely fast. You have to overcome the inertia of the metal rail, but once you do that, you can basically make this thing fire as fast as the current is traveling. In a low resistance device, current travels about 1/10 the speed of light, so you can make it go really, really fast. Super high velocity. Yeah. Would you like to see an animation of the Navy railgun?
Yeah, that's
So this kind of thing exists where if you see pictures or videos of it, somebody else basically made sure that you only saw what you were supposed to see.
Wow.
Now, you've all seen bullets in Hollywood and things. This is important for a very specific reason. Do you see all that steam and heat